it's like, I don't know, it feels so ingrained in us, you
Yeah.
know, like ancient farmers looking at the skies, trying to guess if it's going to rain, or even
Right.
just us in the morning deciding what to wear based on yesterday's weather.
Yeah.
We're always kind of using those past experiences, those similar situations,
Totally.
to get a sense of what might happen. And turns out, in data science, that same intuition, it's actually the basis of a whole category of prediction methods called nearest neighbor methods. And that's what we're going to be diving into today.
It's really cool. Yeah, these techniques sound super simple on the surface. Like just find the things that are most similar, right?
Yeah.
But they're surprisingly powerful for making predictions. And that's what we really want to unpack today. We want to figure out why they work so well, what's the thinking behind their success. And we'll be looking at this paper, explaining the success of nearest neighbor methods in prediction as our guide.
And this isn't just some, abstract concept. You see this nearest neighbor idea popping up all over the place in technology that we use every single day, right?
Yeah, definitely.
Think about like Netflix, how it suggests what you might want to watch next.
Right.
A lot of times it's looking at what people with similar taste have enjoyed.
Yeah.
Or in healthcare, you have tools that might compare a patient's data to similar cases to help doctors make more informed decisions. And even in online learning, platforms can tailor the content based on how other students with similar backgrounds have progressed through the material.
Right.
And all of these, what they have in common is that they're dealing with these huge amounts of data, right?
Huge, yeah.
And where the underlying patterns, they're not always obvious.
That's a great point, yeah.
Yeah.
And a lot of other prediction methods try to learn like a specific formula or like a recipe from the data. But nearest neighbor methods are different. They don't try to build this rigid, recipe. They just look at what happened in the most similar past situations.
Right.
And so that's what we mean when we say that they're often non-parametric. There's no fixed set of rules that you're trying to learn beforehand. And that can be a real advantage when you're working with data where you have no idea what the hidden structure might be.
Okay, so instead of trying to build this grand model, this one-size-fits-all model for all the data, we're basically saying, let's just zoom in on the data points that are most similar to the one that we're trying to understand.
Yep.
But then how do you decide that? What makes two data points neighbors?
That's the million-dollar question, right? And that's actually a big part of what makes these methods so powerful is the flexibility in answering that question.
Okay.
And it comes down to two main things. First, how are we representing our data?
Right.
We call this the feature space. What are the specific characteristics or measurements that we're using to describe each of our data points?
Okay.
And second, how do we measure the distance or the similarity between those representations? And this is where distance functions come in.
Okay.
So for example, if you're looking at houses, your feature space might include things like the square footage, the number of bedrooms, the location, all those kinds of things that we might care about.
The stuff that makes a house a house.
Exactly. Yeah, the characteristics. And then a simple way to measure the distance between two houses in this feature space would be just using standard Euclidean distance. It's like measuring, the straight line distance between 2 points on a graph.
So you're basically plotting them like houses on a chart.
Exactly.
Based on their features, and then just seeing like how close the dots are.
Exactly. But you can get much more sophisticated than that. Like imagine you're trying to compare two streams of sensor data over time. Maybe you're trying to see if two machines are behaving similarly.
Right.
The patterns you're looking for, they might be shifted in time.
Oh, interesting.
Right. So you need a distance function that can account for that.
Okay.
Like it can kind of stretch or compress the time series to find the best alignment before measuring the difference.
Okay.
And there are techniques like dynamic time warping that can do that.
Oh, okay.
And when it comes to actually deciding what those characteristics should be, those features, we can either carefully select them ourselves based on our understanding of the problem, or increasingly, we can use machine learning tools like deep neural networks to learn the best way to represent the data.
Okay, so we've got this core idea of finding neighbors based on how similar they are in this feature space, using whatever distance function we've chosen. But how does that actually help us make predictions? I mean, are we talking about predicting numbers, like in the house price example?
Yeah.
Or are we talking about predicting categories, like whether an email is spam or not spam?
Both, actually.
Yeah.
The paper looks at both of those kinds of prediction problems. Regression where you're predicting a continuous value, like a number, and classification, where you're predicting which category something belongs to.
Okay, so let's start with regression. What's the basic setup there?
Okay, so imagine you want to predict, let's say, the temperature tomorrow.
Okay.
And you have a bunch of data about today's weather, right?
Right.
Like today's temperature, humidity, wind speed.
Uh-huh.
So in this case, your feature vector, we usually call it X, would contain all of those measurements, those weather characteristics.
Okay.
And the thing you're trying to predict, your label, we call that Y, would be tomorrow's temperature.
Got it.
And the underlying goal of regression is to estimate what we call the conditional expectation.
Okay.
Or sometimes it's called the regression function.
Yep.
And this is, think of it as the expected value of Y given a specific set of X features.
So like the average temperature tomorrow given today's weather.
Exactly. Yeah. Like on average, what would we expect the temperature to be tomorrow given these particular conditions today?
Okay.
And you mentioned noise in the labels earlier.
Yeah.
This is a really important point. Real-world data is messy.
Right.
It's not perfect. There's always some inherent randomness or noise involved.
Yeah.
So the actual temperature tomorrow might be a little higher or a little lower than that expected value that we're trying to estimate.
Yeah, that makes sense.
And when we build a prediction model, we're not going to be perfectly accurate all the time.
Right, of course.
One way we can measure how good our predictions are is by looking at the expected squared difference between our prediction and the actual label.
Okay.
This is a common approach. And basically, it penalizes those larger errors more heavily.
So we're really trying to minimize that squared difference. We want our prediction to be as close to the real value as possible.
Exactly, yeah. We want to be as close as possible, especially when we're really far off.
Especially when we're really far off.
Exactly.
Yeah.
Now, there's this important concept called the bias-variance trade-off that comes up when we talk about different prediction methods.
Okay.
Imagine you're trying to hit a target with darts,
Yeah.
right? Bias is like you're consistently aiming off-center.
Okay.
So your darts are clustered together, but they're not hitting the bullseye.
Right. You're consistently wrong in the same way.
Exactly. And then variance is like your shots are scattered all over the board.
Okay.
Even if your aim is, on average, okay.
Right. So it's more about consistency, like how spread out your predictions are.
Exactly. So in a prediction model, a very simple model might have high bias.
Okay.
Meaning it's making very strong assumptions about the data that aren't really true.
Okay.
And that leads to systematic errors. But on the other hand, a very complex model might have low bias on the data it was trained on, but very high variance.
Okay.
Meaning it's so sensitive to the specific training data that it doesn't do well on new data it hasn't seen before.
Right. It hasn't generalized well.
Exactly. Yeah. It's overfit to the training data.
Okay.
So the challenge is finding that sweet spot, right? A model that's flexible enough to capture the real patterns in the data, but not so complex that it just memorizes the noise.
Right. And that it can actually perform well when it sees new data.
Exactly. Yeah. And the choices we make with our nearest neighbor algorithms, like how many neighbors we consider, that will directly affect this bias variance trade-off.
Okay.
Now let's talk about classification.
Okay, yeah, let's switch gears to that.
So here, instead of predicting a continuous number, we're trying to predict which category something belongs to.
Okay.
Like, is this a picture of a cat or a dog?
Right.
So our label, Y, it takes on one of a limited number of discrete values.
Okay.
Like cat or dog. Or often we represent them numerically like 0 or 1.
Right, 0 for cat, 1 for dog.
Exactly. And our goal is to build a classifier that, given a set of features like the pixels in an image, it can output the correct category.
Okay.
Now, there's this really important theoretical concept called the Bayes classifier.
Okay.
Think of it as the absolute best possible classifier you could have.
Okay.
It's the gold standard. The one that makes the fewest mistakes, in theory.
The perfect classifier.
Yeah, in the ideal world.
Yeah.
And there's a fascinating connection here. The Bayes classifier is actually directly related to that regression function we talked about earlier.
Okay.
So in the case of binary classification, meaning just two categories like cat or dog, the regression function, X, it tells us the conditional probability that a feature vector X belongs to class 1.
Okay.
So the Bayes classifier just says, okay, if this probability is 50% or higher, predict class 1. Otherwise, predict class 0.
So if we knew the true probability of an image being a dog,
Right.
given all of its pixels,
Yeah.
we could build the perfect cat-dog classifier.
In theory, yes. The decision boundary for this Bayes classifier, it's where that probability is exactly 50%.
Okay.
But of course, in the real world, we don't actually know that true probability.
Right.
So what we do is we try to estimate that regression function using our training data. And then we use that estimate in place of the true function when we apply the Bayes classifier rule. This is called a plug-in classifier. And as we'll see, nearest neighbor methods, they give us ways to create these estimates.
So whether we're predicting a number or a category, it often boils down to trying to estimate this underlying probability function.
Exactly.
So how do nearest neighbors actually help us do that?
Okay, so let's start with how nearest neighbor methods work for regression. The most intuitive one is called k-nearest neighbor, or KNN regression.
Okay.
The idea is very simple. If you have a new data point that you want to predict a value for, you look at the k-training data points that are nearest to it in your feature space.
Okay.
And then you just average the values of those k-neighbors, and that's your prediction.
So if I'm trying to predict the price of a new house, I find like the 5 most similar houses in my data based on their features, and then I just average their sale prices.
Exactly. That's the basic idea.
Yeah.
Now, how do we decide which houses are nearest?
Right.
That's where our distance function comes in.
Right.
We use that to measure the similarity or dissimilarity between houses.
Okay.
And just for the mathematical theory to work out nicely, we make a small assumption, which is that if there are ties in distances, like if 2 training houses are exactly the same distance away from our new house, we just break those ties randomly.
Okay, yeah. So it's just a way to handle those edge cases where things are perfectly tied.
Yeah, it makes the analysis cleaner. So are you ready to move on to some other ways we can use the nearest neighbor idea?
Yeah. Let's hear some more methods.
All right. So another approach is called fixed radius nearest neighbor regression.
Okay.
Instead of fixing the number of neighbors that we consider, like I, here we fix a radius, which we usually call ash, around our new data point.
Okay.
And we average the values of all the training points that fall within that radius.
So instead of saying, like, look at the 5 closest, you're saying look at everything within this bubble, this radius.
Exactly, yeah. And so the number of neighbors we end up considering, that can change depending on how dense the data is packed around that point.
Okay, that makes sense.
All right, and then there's another one called kernel regression. And specifically, the Nadaraya-Watson method is a common one. This one's a bit more flexible.
Okay.
So instead of giving equal weight to all the neighbors within a certain range, like we do in fixed radius, here we use a kernel function.
Okay.
We usually denote it with k.
Okay.
And what this kernel function does is it weights the contribution of each nearby training point based on how far away it is.
Okay.
So points that are very close get a higher weight in the average, and points that are further away get a lower weight.
Okay.
And we also have a bandwidth parameter here that controls how wide or narrow that weighting function is.
Okay.
So the nice thing about kernel regression is you have a lot of flexibility in choosing different kernel functions.
Okay.
You know, depending on what assumptions you want to make about your data, different kernel functions might be more appropriate.
So it's like a smoother, more gradual kind of averaging.
Yeah, that's a great way to think about it. Yeah.
Where the really close neighbors get to have a bigger say.
Yeah. Exactly. Yeah, they have more influence on the final prediction.
Okay, and then how do we take these regression ideas and apply them to classification problems?
Right. So we talked earlier about that idea of a plug-in classifier.
Yeah.
So basically, we can take the regression estimates that we get from these nearest neighbor methods, KNN, fixed radius, kernel regression.
Okay.
And we can plug those into that Bayes classifier rule.
So instead of just getting a number out, we're using that number, which is like our estimate of the probability of being in a category to make a decision.
Yep.
Like a yes-no or a cat-dog decision.
Exactly, yeah. So for example, in KNN classification, you find the nearest neighbors to your new data point. You look at what category each of those neighbors belongs to.
Okay.
And you predict the category that has the majority vote among those neighbors.
So it's like each neighbor gets a vote.
Exactly, yeah. It's like a little election. And in kernel classification, it's similar, except that the votes are weighted.
Okay.
So each training point that falls within the kernel's reach gets to cast a vote. But the strength of that vote is determined by the kernel function.
So those closer points, they get a stronger vote.
Exactly.
Okay.
Now, you mentioned earlier that there's a whole body of theory that helps explain why these methods, which seem on the surface pretty simple, can be so effective.
Yeah.
Can you walk us through what kind of guarantees do we have?
Yeah, absolutely. And this is where the research gets really interesting, I think. So the paper focuses on what are called nonasymptotic statistical guarantees.
Okay.
And what that means is instead of just telling us what happens in the limit, when you have an infinite amount of training data.
Yeah. Which never happens in the real world.
Exactly. These guarantees, they give us a much more practical understanding of, okay, how much training data do we need?
And how should we choose the algorithm's parameters?
Okay.
Things like K or that radius H.
These are the things we get to control.
Right, exactly.
Yeah.
How should we choose those in order to achieve a certain level of accuracy, even when we have limited data?
Okay. So it's less about the theoretical limit and more about like what we can actually expect to see in realistic scenarios.
Exactly. So let's think about K-N-N regression at a specific test point X.
Okay.
The theory provides us with error guarantees.
Okay.
And these guarantees, they depend on a few conditions. So first, there are some technical conditions about the space that our data lives in and how the data points are distributed in that space. And then there's a condition on how smooth the true underlying pattern is that we're trying to predict.
Okay, so by smooth, you mean like it doesn't jump around erratically?
Exactly.
Yeah.
So if the thing you're trying to predict, it changes wildly, even with small changes in the features, then nearest neighbors might need a lot more data in order to give you accurate predictions.
Right. Because there's not a clear pattern to pick up on.
Exactly. And the core idea behind the guarantee is that we're trying to balance two potential problems.
Okay.
The first problem is that if we don't look at enough neighbors, if K is too small, our prediction might be too sensitive to noise in the individual data points.
Okay.
Right?
Yeah.
Like if we're only looking at one neighbor and that one neighbor happens to have a really weird value,
right.
then our prediction's going to be way off.
It's going to be skewed by that.
Exactly.
Okay.
And then the second problem is that if we look at too many neighbors, meaning K is too large, the neighbors that we're averaging over might be too far away from our test point X.
Okay.
And therefore not really representative of the true value at X.
So we need to find this balance where we have enough neighbors to smooth out the randomness. Yeah. But those neighbors also need to be close enough to be relevant.
Exactly. Yeah. We need to strike that balance.
Okay.
And the theory tells us how to choose K and how much training data we need in order to kind of minimize the probability of these two bad events happening.
Okay.
And therefore ensure that our K and N estimate at that point X is close to the true value.
But that's just at one specific point.
Right.
What about like the overall accuracy, like on average?
Right. So for that, we think about what's called the expected regression error.
Okay.
And the theory talks about these regions of the data space where the data is more well-behaved.
Okay.
We call these sufficient mass regions. These are regions where we have a decent amount of data.
Okay.
And if the point that we're trying to predict for, if that point falls into one of these good regions, then we can expect that with enough training data, our K&N prediction will be pretty accurate on average.
Okay.
Now, the analysis also takes into account the bad regions where the data might be more sparse, but the probability of our test point actually landing in those bad regions, that's factored into the overall expected error.
So it's harder to make strong guarantees in areas where we just don't have as much data.
Exactly, yeah. That's very intuitive.
Okay. And what about fixed radius NN regression? Is the theory similar there?
It's similar, yeah.
Okay.
The key there is choosing the right radius H.
Okay.
So if H is too small, you might not find enough neighbors to get a good average.
Right.
If it's too large, then you might include points that are actually quite different from your test point and have very different labels.
Right.
So again, the theoretical guarantees connect the choice of H, the amount of training data, and that smoothness of the underlying pattern to the expected error.
Okay.
They all kind of play together.
And what about kernel regression?
Yeah.
Does using that weighting function change things?
It does. So kernel regression gives us more flexibility in how we weight the nearby points. But it also introduces another parameter to tune, which is the bandwidth of the kernel, H.
Oh.
So in general, the theoretical guarantees for kernel regression They also depend on the choice of kernel function, the bandwidth, the smoothness, and the data distribution. It's a little bit more complex. And there's an interesting result here for a very simple type of kernel. One that basically gives a weight of 1 to all points within a certain radius and 0 to those outside. The theoretical guarantees for kernel regression can actually sometimes be weaker than those that are derived specifically for fixed radius NN regression. In terms of how much data you might need. But the kernel regression framework, it's more general. And it allows for more sophisticated weighting schemes.
So it seems like there's some fundamental assumptions about the data and the patterns we're trying to find that underpin all these guarantees.
Absolutely. The paper highlights a couple of key sets of assumptions.
Okay.
One set, they often call it a technical, it basically ensures that the data space and the way the data is distributed, they're mathematically well behaved, which allows us to rigorously talk about probabilities and expectations. And then the other set, they call it ADK, is more specific to kernel regression.
Okay.
And it basically puts some conditions on how quickly the kernel function's influence decreases as we move away from the test point.
Okay. Okay, so that gives us a sense of the theoretical foundations for regression.
Right.
What about classification? You mentioned earlier that we might not need such strict assumptions there.
Yeah, that's right. So for classification problems, it turns out we can often achieve good performance with nearest neighbor methods under somewhat weaker conditions than what's typically required for regression.
Okay.
And specifically, we can sometimes relax that requirement that the underlying probability function be super smooth everywhere.
Okay, and why is that?
Well, think about it this way. For classification, our main goal is usually just to get the category right.
Right.
We don't necessarily need to know the exact probability that something belongs to a certain class.
As long as you know which side of the line it's on.
Exactly.
Yeah, that's good enough.
As long as we can correctly figure out, okay, is this more likely to be a cat or a dog?
Yeah.
We've done our job.
Right.
The percent value of that probability, it's not as critical.
The exact percentage doesn't matter as much.
Exactly. And this leads to the idea of a margin condition.
Okay.
So imagine you have, the boundary between, say, spam and not spam emails.
Okay, yeah.
This boundary, it's not always a sharp line.
Right.
There might be a fuzzy region where it's kind of hard to tell. And so the margin is essentially the width of this fuzzy zone.
Okay.
And the margin condition, it describes how quickly the probability of being in that uncertain zone decreases as you move further away from the boundary. So a larger margin, meaning that uncertainty decays very quickly.
Okay.
That generally makes the classification problem easier for any method, really.
So if the categories are very well separated, like if there's a clear gap between them, it should be easier for a nearest neighbor classifier to figure out what's what.
Exactly. And under these more relaxed assumptions, including this margin condition, we can get theoretical results about the consistency of nearest neighbor classification methods.
Okay.
Like KNN. And consistency here means that as we get more and more training data, the error rate of our classifier, it gets closer and closer to the error rate of that best possible Bayes classifier we talked about earlier.
It gets closer to perfect as we get more data.
Exactly. But there are some interesting caveats here. There are also some theoretical findings that suggest that under certain conditions, KNN classification might not always be what we call uniformly consistent.
Okay, interesting. So it's not a foolproof guarantee. Exactly. Every single situation.
Yeah, there are some subtle details there. But the overall picture for classification, it tends to focus a bit more on how well separated the categories are, rather than just the overall smoothness of that probability function.
Okay. Now, the paper goes on to discuss some specific applications.
Yeah.
Where are these nearest neighbor methods being used to solve real-world problems?
Right. So one really fascinating area is time series forecasting.
Okay.
So imagine you're trying to predict, is this news story going to go viral on Twitter?
Okay, yeah.
You can look at patterns of how similar stories have spread or haven't spread over time. And